All right, perfect. Then I hope everybody can see my screen.
We do.
And also see my face. And then I'm ready to go. So yeah, first of all, thank you very much for joining. Super happy that we have so many listeners and so many participants today as well. Same like yesterday. We already heard a lot of interesting topics today from the EL 4.0 and the integration parts and now the partner training. And now I want to start with our final presentation, the AAM cluster. So I hope you are excited about that as well. I'm Philipp Endres. I'm located in Germany, also part of the customer support team. And yeah, I'm happy to introduce you to this topic today. Questions will be answered at the end again, like with the previous presentations. So let's go. So first of all, a little overview about the topics that we're going to discuss within this presentation. So first, I want to introduce you how to set up an AAM cluster. We will talk about the two different variations. So we have the air-cooled version and the liquid-cooled version. Then we're going to talk about experiments and findings from our Enapter lab, where we build up an electrolyzer cluster with 5 units. We go a little bit more into detail about especially the liquid-cooled. And then finally, some details, what you need to consider when you are purchasing the electrolyzer liquid-cooled version and when you stack those modules together, but also additional things that you need to consider. All right, you already know, I guess, that the AAM stack is used either in the AAM electrolyzer or in the multi-core. We will hear more about the multi-core tomorrow. So for today, I would like to focus on the upper path. So the AAM electrolyzer can be used, of course, in a cabinet. So just stacking several electrolyzers on top of each other, use them in a cabinet. And then, of course, you can also combine several cabinets to store them together, for example, in a container, depending on your individual hydrogen solution. So why do you want to do that? So one important point is we already had this topic today a little bit. So with the electrolyzer 2.1, you have a little limit of the production rate because it can be operated between 60 and 100%. And when you are stacking several modules together, of course, depending on your specific use case, this production rate in percentage-wise will increase. So you will then have the possibility, for example, with 3 electrolyzers to produce hydrogen from 20 to 33% and then 40 to 100% compared to the 60 to 100% that you have with one electrolyzer. Now I would like to show you what is possible with a 20-foot container. So therefore, we calculated how you can produce hydrogen in a foot container, either with the AAM Cluster 60 or the AAM Cluster 70. So the AAM Cluster 60, for example, is able to produce 64 kilograms of hydrogen per day. So you're stacking 60 electrolyzers in a container. Additionally, you will add some dryers, and then you can reach a purity of 99.999%. On the other hand, if you think 99.9% hydrogen purity is enough for you, you can produce up to 77 kilograms of hydrogen per day. Please be aware that these are just drafts. So of course, it depends on your individual setup, how you want to integrate your modules into the container, what else or additional stuff you will need. Now I would like to talk about the air-cooled versus the liquid-cooled electrolyzer. So both modules are very similar. However, there are some little differences. So for example, the air-cooled electrolyzer is easier to set up because you don't need any additional equipment for your cooling cycle. It has a huge fan included, which is automatically cooling down the electrolyte inside the unit. It's advantageous for strongly air-conditioned rooms and containers. And also, if you have semi-open containers, you can use the air-cooled version as long as you are in warmer environments. Please be aware that the electrolyzer is not able to survive temperatures below 2 degrees. So if you have freezing conditions, then make sure your room or your container is especially is equipped with a special air conditioning system, which is providing enough heat for not letting the electrolyzers freeze too much. On the other hand, if you are using the liquid-cooled electrolyzer, you have the possibility to easier manage the waste heat. Also, a compact stacking is possible, as we already heard it before in Max's presentation. So the liquid-cooled electrolyzer can be put closer to the wall. So that means the space behind the units can be decreased. Also, in some specific cases, it is possible to use the heated water which comes out from the electrolyzers. So you're feeding the liquid-cooled electrolyzers with cold water, and then warm water comes out. However, I put that in brackets here because it really depends on your specific application. And in many cases, it either might not be possible or it might not be efficient. So please consider that. Now, let's talk a little bit again about the interfaces. Max also mentioned that in detail, so I don't want to repeat everything, but just as a quick repetition for those who could not join earlier. So we have different interfaces in the electrolyzer. In this case, you can see the liquid-cooled version, which has these 2 additional cooling water in and outlets. But what you have in all electrolyzers is the H2O in, the O2 vent, the H2 out, and the H2 purge line, which is now called H2 vent in the EL 4.0. But it works very similar. So those inlets and outlets, they can be combined together for several modules. Please remember to use a water trap for the O2 vent line and the O2 purge line. And please also make sure that you dimension your pipes accordingly to the number of electrolyzers. So in the liquid-cooled version, you have the additional inlet and outlet, as I already said. We will take a further look into that in the next slides. Of course, all the units need to be power supplied. And what I want to mention here again is the Drycon connector, which sits over here. So with this Drycon connector, it is possible to place a hydrogen sniffer in the top of your cabinet or your container. And then once it triggers, because it detects hydrogen, all connected electrolyzers, which can be connected in serials, they can be switched off automatically when this sniffer is triggering. Okay, let's take a look how the opening and closing cycle in the liquid-cooled version looks like. So what you can see here is a diagram where this is actually from our dashboard, so everything that you can see online. And we have here a temperature curve. So you can see this wave pattern, which means that the temperature of the electrolyte within the electrolyzer is here roughly between 55 degrees and goes down to 53.20 maybe. So once the valve inside the electrolyzer liquid-cooled opens, then cool water is flowing through the electrolyzer and allows the electrolyte to cool down. Once it reaches 54.6 degrees, the valve closes. But because of hysteresis, and because this sensor, which is measuring here the temperature, is put downstream, so downstream of the stack, so after the electrolyte is heated, we have a longer cooling down phase. And what we want to make sure is that the electrolyte is always between 53 and 55 degrees. So yeah, that's basically here visible. What we can also see in the yellow line is that we have a small increase. So this is due to the cooling cycle in this specific experiment is a little bit too small. So please be aware that when you are building up your cooling cycle, then dimension it properly so that the electrolyzer is also able to reach the 53 degrees. In general, the cooling cycle length depends on the cooling temperature, of course, but also the flow rate. So when we look a little bit out, like zoomed out, we can see some differences. And we have here the liquid cooled on the left side and the air cooled on the right side. And this is also a picture from our telemetry. And we can see here in the lowest graph, the temperature again, then above that, the voltage signal of the stack and the stack current. And on the left side here for the liquid cooled, we can see that the temperature is here toggling between, I would say roughly 53 and 55 degrees. So that's a delta of 1.94 degrees, while the temperature on the air-cooled side is way more stable at 0.06%, 0.6 degrees. But that's all in the range. So only what we can see is that we have this typical sawtooth pattern on the liquid cooled versus, a more, random pattern on the air cooled, let's say. So what has to be considered when you set up your cooling liquid and cooling cycle? So here in this diagram or in this graph, we can see that the flow rate depends a lot on the position of the electrolyzer. So when we imagine that we have several electrolyzers stacked on top of each other, and those electrolyzers are provided via the same pipe, which then splits up individually, then we can see that there are quite some differences in the flow rate depending on the position. So the electrolyzers which are on the bottom of the cabinet, they receive a higher flow rate than the ones on the top. And this is quite crucial because what needs to be ensured is that the flow rate is sufficient also on the top. And when we think about that a little bit further, we will also see it in the next slides, is the more electrolyzers we have, the more challenging this topic becomes. All right. So when we have lower flow rates, we can already see a difference. But when we then think, okay, let's just increase the flow rate and so to say, make sure that we also reach a specific flow rate in the upper electrolyzers, this is not actually 100% solving the problem. What we can see is more turbulences in the lower electrolyzers, but only a small increase in the higher electrolyzers. And here we also have like these dark blue areas, which are increasing. So that's not really what we want. So we have to ensure that we have a sufficient flow rate in all pipes and also that our pump is available and is able to provide the pressure needed. Also, I want to talk about pressure drops. So the higher the flow rate, the higher the pressure drops. So give me a second, I'm not sure if you can see that. So when you have a flow rate between 1 and 2, then we're in an almost linear phase. So around this 1 to 2 liters per minute flow rate, we are very good. But then when we increase the flow rate, we see that the pressure drop grows exponentially. So what does that mean? If the pressure drops exponentially, that also means higher pressure drops are making the system more inefficient, okay? And that's, of course, something that we want to avoid. So, yeah, just due to the friction of the pipes, we see that the pressure drops more and more. And so we found out that the perfect range is around about 1 to 2 liters per minute that we want to reach here. Next, let's talk about flow restrictors, because this is the solution to our next problem. When we don't use any flow restrictors and we're just opening the valves inside the electrolyzers sequentially after each other, we can see that the flow rate is quite stable like at 9.5 liters per minute. Please be careful. In this case, the electrolyzers are opening after each other. When we do that at the same time, and we're opening more and more at the same time, we can see that the flow rate drops to around about 3.5 liters per minute. So that was expected, right? But what is the problem here is that we can see a difference between the gray and the blue graph. And the thing is that this actually is showing again what we saw in the slides before, that if you have electrolyzers which are positioned in the bottom of the cabinet, like the blue one here, you will have higher flow rates than for the gray one, which is positioned in the top of the cabinet. Yeah. So the challenge is here to find a solution how this uneven distribution of the cooling agent is solved, and every electrolyzer is receiving the proper amount of cooling agent to be properly cooled. So when we installed flow restrictors, we saw that this is way more equal. So we have a constant flow rate of 2 liters per minute, and that's, so to say, perfect. By the way, if you're wondering why the red curve here is a little bit higher, this is due to a little defect in the flow restrictor, but it is not related to the electrolyzer, because we found out if we're just switching the flow restrictor, we will have that higher curve in another electrolyzer. But what we can see here at the end is, again, that it doesn't matter how many valves are opening at the same time, how many electrolyzers want to be cooled at the same time, the flow rate is very, very stable at 2 liters per minute. So that's perfect. We really see the effect of the flow restrictors. So we definitely recommend to use them. Now let's look a little bit more in detail to the volume flow and the cooling temperature. So here we have like some 3-dimensional graphs, and we already found out that the minimum necessary flow rate is about 1 liter per minute. So what can we see here in these graphs? So on one hand, we have these dark gray bars. Those are the ones where the cooling power is not sufficient. So we have very little volume flow, and it is at 0.1 liters per minute. It is basically, it doesn't matter how cool the water is, it is not sufficient. Yeah? But of course, the higher the temperature, so these are the bars in the back, the higher the temperature, then the minimum temperature, which is the stack reaching, is also higher. On the other hand, if we're using very cold temperatures, like for example here, these dark blue bars, which are having a temperature of 3 degrees, here the stack reaches 51.95, so almost 52. That's too low, because we have to have a stable temperature of around about 53 to 55 degrees. So we need to look a little bit here more in the middle of these graphs. And when we are looking to these 1 to 2 liters per minute, then we can see, okay, we are somehow in this range, and then we have cooling temperatures of around about, let's say, 16 to 30 degrees. We are recommending here 6 to 40 degrees. So that's the total range that you potentially could use, but yeah, perfectly is around about 20 to 25 degrees. Now let's look on this graph on the right side. Here we are analyzing the opening valve time, and we can see again that these bars on the left side and in the back, the dark gray ones, they are not sufficient cooling. So the valve, it doesn't matter how long it is open, it cannot provide enough cooling power for the electrolyzer. And here again, we are in a perfect range in the middle. So for example, when we are looking here in the red bar, so this, which is having the 35 seconds opening valve time, then we can already see, okay, we are having here about 41 degrees Celsius of the cooling agent temperature. And even if we have 1 liter flow rate, then these 35 seconds, they're quite long. And the thing is, we are using a normally closed valve. So it consumes energy as long as it's open. And so shorter opening times is also more efficient. Yeah. So that means if we're like more in these, let's say, yellow or greenish bars, then we are in the perfect range. So that means we are having an optimum valve opening time of 10 to 20 seconds. And what I also want to show here is we need to find a balance between efficient cooling and a wear out of the electrolyzer valve. Because the more often we close and open the valve, of course, the quicker it wears out. On the other hand, we want sufficient cooling and we want to build up this cooling cycle in an efficient way, which also considers pumps and all the other devices that we're now taking a look to. So what additional devices do you need when you want to set up your cooling cycle? You need a pump, at least one. I will show you in the next slide that 2 are even better. You need a pipe cutter. You need some LLDP pipes or other pipes which are compatible. And please be aware that also for your cooling loop, you need to dimension them appropriately, right? So when you're having bigger systems, make sure that the pipes that you're using have the diameter which is sufficient for providing enough cooling flow and then also enough cooling power, so to say. It is generally advisable to use vent valves and a little bit of transparent pipe to see air bubbles coming up. So it's basically unavoidable to have air in your cooling cycle. And this air makes your system inefficient. So what you want to do is you want to install vent valves on the top of each of the cooling cycle to be able to release the air and other maybe oxygen or other gas components in your cooling cycle to leave the loop so that it is not decreasing your efficiency. Then you have a bypass valve. This is also recommended because it allows you to have a closed cooling loop. We will see that in a second. And a damper device to avoid this water hammer. So you can imagine you have several electrolyzers. They're closing the valves at any time. This might also be somehow randomly. I mean, it is very difficult to match that to each other. And then you have very uneven flow rates all the time. And to avoid this water hammer, it is very useful if you have a damper device. So let's take a look how a possible setup could look like. I hope this is not too complex for the non-engineers in this session, but I'm trying to explain it very roughly and somehow clear, hopefully. So on the left side, you basically have the cooling cycle. So you have a storage where you store your cooling liquid. Then you have one pipe which is connected to your chiller to cool down the cooling agent. Then you have a pump, an additional pump, which is pushing in the water or whatever cooling agent you're using and provide that cooling agent to the electrolyzers, which are here on the right side. What you can also see is that before each electrolyzer, you have the flow restrictors that are also visible here in this upper picture. And in this case, we also put flow meters on the outlet to get a better understanding. But yeah, this might not be needed in every scenario. So, but yeah, the flow restrictors, they definitely make sense. So I want to mention them here. And then what else? We have here the damper device that I was already talking about. We have the bypass valve, which is here. And then, of course, we have the other interfaces like the H2 purge line, H2 outlet, and so on and so forth that we were talking about before. And so this is how your setup could look like. Of course, you can make it more complex. Of course, you can make it more easy. What I want to focus here is we have this closed cooling loop here, which is possible because we have this bypass valve. If you don't use a bypass valve, then you will actually have to figure out about the pressure in your pipes to make sure that none of the electrolyzers is reached by either too high or too low pressure. Remember, we need a specific cooling power. And on the other hand, we also don't want that the pressure is too high. Yeah? So that's very important. Of course, you can put, as I already said, additional pressure or temperature indicators. And depending on your individual setup, you might need additional devices, but these were the ones that we used in our setup at least. And yeah, they are the basics. So let's summarize again. What we found out in our experiments. We have an optimal feeding temperature of 20 to 25 degrees. This temperature can be extended to 6 to 40 degrees. However, it depends on your individual setup. It depends on the efficiency and also on the components that you're using. For example, the pumps. Please remember that the pumps are providing enough pressure, but at the same time are not damaging or overpressurizing the pipes. Please also ensure that your pipes are dimensioned appropriately. We have a perfect cycle duration of around about 100 seconds. Then, so sorry to say, so the cycle duration is, so to say, the time from the moment when the valve opens the first time, then it closes until it opens again. So the full cycle around about 100 seconds. We have an optimal flow rate of 1 liter to 2 liters per minute. The valve opens between 54.6 degrees and 55 degrees because we want to reach a perfect stack temperature of 53 to 55 degrees. Now, last but not least, let's talk about suggested applications for the ELLC. We already talked about the specialties of the liquid cooled and that you will have to investigate what makes the most sense for your individual scenario. So the liquid cooled electrolyzer is especially relevant when you already have an existing cooling cycle where you can just attach additional electrolyzers. Also, you should have some competences about liquid cooling and flow rates in your company. Available temperature ranges should match the requirements. So it also depends in which area, in which climate zone you're erecting your stacks and your container. And please, as I already said, be aware of cooling and freezing temperatures. So we have specific temperature ranges where the electrolyzers can be operated and stored in. Please make sure that you don't exceed them. These are from 2 to 45 degrees, but you can see all these details also in the data sheets and in our manuals, of course. The liquid cooled system makes especially sense if you have bigger systems, because then also more heat is generated and those heat is more likely to be used. In some cases, it might be possible to also couple heats with fuel cell and energy storage, also depending on your specific application. Or if you have sector coupling, for example, a heat network. So that's it. Thank you very much for listening. Please contact us for any questions, for feedbacks, for problems, for requests. You can write to enapter@support.com whenever you want. Also, you can find a lot of information online. We will talk a little bit more in detail about that tomorrow. And yeah, so far I'm looking forward for your questions. And the next step is now to see what you wrote in the chat. So I'm already very curious about it. So let me take a quick look. I have to check out where it starts. Please hold on. So I think the first question here is from Denise Duda. If we combine multiple electrolyzers, we need to increase the pipe diameter. But if we install a dryer in the system, we need to go back to 6 millimeter diameter because its inlet is 6 millimeters or a quarter inch. So increasing the connected lines becomes meaningless. I'm missing something. Okay, so we will need to make sure that we're talking about the right things. So the quarter-inch pipes are our stainless steel pipes, which are used for the hydrogen outlet or the hydrogen purge line. And those diameters are the same for the electrolyzer and the dryer. However, when you are using, for example, a water tank and an electrolyzer, or when you're using the liquid-cooled version and especially some older components of us, then you will have maybe different diameters of the LLDP pipe. Yeah, so that's something where you need to consider the diameters. If you have more questions about that, just let us know. Then let's see, next questions. So Arthur Scheffer is asking, what kind of flow restriction are you using? Honestly, I don't have that currently here. I will have to look that up. So please send us an email and then we are happy to answer you that by email. What else? Diana Duque, I hope I'm pronouncing it right. I'm sorry. So your recommendation is to secure that the flow rate is 2 liters per minute per electrolyzer with a pressure of 2 bar. Yes, exactly. So that's the perfect conditions. I would say it also, of course, depends a little bit on your setup. So we don't say strictly, okay, this and this are the values that you need to have. So of course, there's also some little flexibility in that. However, these are the values to use when you want to dimension your system roughly. Timothy Crofts is asking, will overcooling have an impact on stack lifetime? Not really. The problem with the cooler temperatures is that the stack is losing its efficiency. So the stack works best between 53 and 55 degrees, as I already said. And when you provide cooler temperatures to the stack, then it will just decrease the efficiency. That's why it is to be avoided. Diana, again, what are the specifications for the cooling water? Is it recommended also to use water? So the specifications of the cooling water, they're actually not so high. So you can use normal water. You can also use other cooling liquids, but please make sure to ask us which one you want to use because, yeah, we tested our systems with water and there might be some incompatibilities. So if you want to use another cooling liquid, then please let us know before to make sure that your cooling liquid or cooling agent is compatible to the system. Oh, thank you very much. I just received an internal note that the email address is wrong. So of course it's support@enapter.com, not the other way around. Thank you very much for the people, in this case, my colleague Stefan, who was very awake and saw this. And sorry for those of you who already wrote to the wrong email address. I hope it's correct now. Denise Duda is asking, if we combine multiple electrolyzers, we need to increase the pipe diameter. Okay, sorry, I already answered that one. Also that one. Thank you very much. Then what else? Arthur Scheffer is asking, if every electrolyzer is using 1 liter per minute, does the total flow summarize with more ELs, like 4 ELs, give a total flow, pump flow of 4 liters per minute? Roughly, yes. However, we said that the 1 liter per minute is really the minimum. So you should be in the range between 1 and 2 liters per minute. So yes, you can roughly calculate with 2 liters times the number of electrolyzers. So if you have 4 electrolyzers, for example, 4 times 2 is 8 liters per minute. So yes, you should make sure that your pump is able to deliver these amount. However, sometimes it could make sense, especially if you have several stacks, several cabinets, each of them with 4 or 5 electrolyzers, that you use maybe a pump for each cabinet, or that you don't have one big pump to provide pressure to all the electrolyzers, but to split it up a little bit and use several smaller pumps instead of one big one. It depends on your setup. I cannot say for sure that this is not possible. However, maybe it is easier to set up and more reliable to not use only one big pump, just because you want to make sure that the pressures are within the specific range. Mauro Cesana is asking, which is the efficiency of the electrolyzer and how is it calculated? So I think this is a typical BD question. However, regarding the efficiency of the electrolyzer, you can find some basic information in the datasheet, of course. Also, when you look into the handbook, so handbook.enapter.com, there you can find more information, especially in this case, you will want to look up into the knowledge base, and there we clarify topics like that. And there we also describe, okay, efficiency, what is meant with it, how do you need to calculate it, etc. Then, Joe, do you provide a chiller? No, actually, we don't provide chillers. Our products are the electrolyzer, the dryer, the water tank module. These are our main components. Of course, we're also providing the software to these products, but a chiller is currently not in our product portfolio, and it is currently also not planned to sell any chillers. I think when you are interested in chillers, it will be recommended to contact one of our system integrators, for example. If you want, feel free to contact us. We will provide you an email address or contact, and our system integrators are happy to help you out with chillers or everything that you need for your individual hydrogen setup. Then Armando Izquierdo, Colorado, is asking, are these clusters creating ATEX zone? So I'm not an ATEX specialist, so I really want to avoid answering this question in detail. However, for the AM cluster, we are having the same scenario like for an electrolyzer, right? So yes, we have additional components, for example, the bypass valves and so on that I was talking about before, but the AM electrolyzer which is used is the same one that we sell in a single one or in multiple ones. So there is no difference in that. Carlos Enrique Manquillo. Philip, is it possible that you share material related to complete sizing of the project, steps, tips, or similar, for instance, according power required, what other calculations are required? Yes and no. So this presentation was to give you an overview about what you need to consider to also help you to somehow get an idea of what are all the things that you need to consider when building up such a cabinet. Yes, of course, we can give you tips. We can give you a lot of help with calculations, etc., etc. Please contact us. Write to support@enapter.com. We can also set up a meeting to talk about those in details. So Denise is asking, I'm talking air-cooled version, steel H2 outlet lines. Can we please get a more specific answer? Yeah, so the air-cooled version is the same like the liquid-cooled version. They both have the 1/4-inch stainless steel pipes, also both for the hydrogen outlet and for the hydrogen purge line. And yes, if you want to combine several electrolyzers together, you have to consider, okay, we will have 500 normal liters per hour as the hydrogen production rate. So 5 electrolyzers, it sums up to 2,500. And the more electrolyzers you are stacking together, the bigger must be your stainless steel pipes. And that also means that if you're running your electrolyzers at 60%, you will have different hydrogen production rates than at 100%, of course. If you want to go a little bit more into detail, let's talk about your individual setup, how many electrolyzers you're talking about. We can answer that, of course. However, I don't want to give general statements because I don't have the calculations here now. So I think it's better to do that in a separate session. I hope that's fine for you. So Carlos Enrique Manquillo, for cooling water is necessary consider pH, hardness, silice, and other parameter. Yeah, yes and no. So of course, the cooling loop is like any other system. It needs to be maintained. Yeah. So if you're using a cooling loop for several months, several years, of course, there could be particles remaining in it. So of course, it makes sense to clean it from time to time. And of course, the cleaner the water, or the better quality of your cooling agent, the less maintenance work you have to do with it. Yeah, I think that's pretty clear. However, I cannot give you any general statements on that topic because, as we already heard it in the previous presentations as well, it highly depends on your water that you provide. And the purer it is, the less maintenance you have in general. However, if you have specific questions about that, then please contact us separately again. Louis Stone is asking, on which topics is Enapter working on research and development? What do you think about the future of electrolyzer? I think that's a little bit off topic, or at least not directly related to this presentation. So I would like to postpone the answer of this question to a later point of view. We will have a very interesting session tomorrow as well. I think your question fits better there. However, we are working on various topics in research and development. Of course, we want to further improve our products in all kind of aspects. We want to make it even more user-friendly. We want to make it even more reliable, more efficient, and so on and so forth. I think as an engineer, there's always something that you want to improve. And very interesting. We're working on a lot of topics in parallel. I'm looking forward to hear your question tomorrow again. Then we have the experts also from BD side, and they can answer your question even better. Viakumar KP is asking, is there a safety device inside the electrolyzer which makes it shut down if the temperature shoots up? So yes, the electrolyzer has several temperature sensors. They are observing or controlling the temperature all the time. And if the electrolyte, which is the processing liquid inside the electrolyzer, is getting too hot, then the electrolyzer automatically shuts off. So now the thing is, with the liquid cooled and the air cooled, of course, it's a little bit differently. With the air cooled version, okay, we have the possibility to increase the fan speed to just, make the cooling power stronger, and therefore cool more. However, if we are already on the edge, so let's say we're in a super hot environment, the cooling fan already works at maximum, and there is not enough cooling power possible, then the system will automatically shut off. In the liquid cooled, of course, we are relying on the cooling cycle. So if you don't provide enough cool liquid, or maybe if you're suddenly changing the temperature of your cooling agent and provide super hot liquid, then this will disturb the system. And it will notice as well that the temperature is too high and it would also shut down. However, our liquid-cooled electrolyzer is not designed for providing very quick changes in the cooling agent temperature. Yeah, so of course that can also always change a little bit, and of course we're heating it up, and there are external factors who are also influencing the temperature. But as long as you're not changing it from, I don't know, 15 degrees to suddenly 35 degrees, I don't even know how that's possible, but maybe you have such a scenario. Then maybe let's talk about that in detail to make sure that the components are not suffering from that. Then let me check if there are any questions remaining. I already answered that one. So yeah, I think those were most of the questions for now. There is one more coming in from Armando Izquierdo, Colorado. Can I use glycolic water for the cooling system? So there are different cooling agents which are possible for usage in the liquid-cooled electrolyzer. However, it also depends on the mixture that you're using. So if you're using pure, in this case, glycolic water, or if you're in which percentages you're mixing it. So please write us an email, and then we can discuss that really in detail without having now the issue of a misunderstanding. Eduardo Rodriguez, how much energy is required for the cooling system? A rough indicator, for instance, in kilowatts per electrolyzer. I think we somehow faced that question in the system integration part. I will have to look up that in the data sheet. So sorry for not being able to answer that one as well. Please write me an email to support@enapter.com. We will answer it very quickly. Yeah. All right, then I think that's it for now. I hope it was very interesting for you, and I hope you learned something new, and I'm looking forward to see you tomorrow for our third and last day. We will have another very interesting presentations tomorrow, and yeah, then at the end of the day, we will also have a session where yeah, the people who registered before have the possibility to pitch for a minute. So very looking forward to that. So, but that's it for today. Thank you very much for your attention. Thank you very much for joining, and looking forward to see you again tomorrow. Thank you.